In the last presentation, we looked at the process for sequential circuit design and even created a simple sequence recognizer. In this companion presentation, we'll look at how to expand on this design to make it better. We can use the sequentially assigned gray code or a one-hot code for the sequence recognizer design. The gray code makes it easier for the next state and output functions to be placed on a Carnot map. Here we see the state table in gray code form with the previous states of A, B, C, and D replaced by their respective gray codes. Here we see the state table for the one-hot assignment. A, B, C, and D are replaced by the codes 100, 0100, 0010, and 0001. We also replace the next state code. In this table you can see how the one-hot assignment makes it easy to determine which state is active. Now let's look at how we can implement these two state tables using D flip-flops. The gray code makes it easier for the next state and output functions to be placed on a Carnot map. Two flip-flops are needed to represent the four states. We obtain the flip-flop input equations from next state values listed in the table, and the output equation from the values of Z in the table. These equations can be expressed as the sum of minterms for the present state variables A and B and the input variable X. Since we're using gray codes, it's pretty simple to minimize the equations using a Carnot map as shown here. We can then implement the logic diagram for the gray code sequence recognizer with D flip-flops. The input gate cost for the combinational logic is 9, and a rough estimate for the gate input cost of each flip-flop is 14. So that gives a total gate input cost of about 37. Now let's look at the competing design. For the one-hot code design, we need 4 flip-flops. Again, we'll be going with D flip-flops. Now we need to derive the flip-flop input equations from the state table. Although state codes listed have values for the 4 variables, recall that when the equations from one-hot code are written, only the variable with value 1 is included. Also recall that each term of the excitation equation for the state variable y is based on a 1 value for the variable y in next state code entry, and the sum of these terms is taken over all such 1s in next state code entries. From here we can derive the rest of the flip-flop input equations and the output equation. We obtain the output equation from the location of the 1 values of Z in the output table. The resulting flip-flop input equations and output equation are shown here. Here we see the implemented logic circuit from the 4 equations on the last slide. The gate input cost of the combinational logic is 19, and the cost of the 4 flip-flops using the previous estimate is 56. This gives a total gate input cost of 74, which is almost twice that of the gray code design. One-hot design tends to be more costly, but it also supports factors such as performance, reliability, and ease of design and verification. States that are not used in specifying the sequential circuit are not listed in the state table. In simplifying the input equations, we can treat the unused states as don't care conditions. The state table here defines 3 flip-flops A, B, C, and 1 input X. There is no output column, which means that the flip-flops serve as outputs of the circuit. With 3 flip-flops, it's possible to specify 8 states, but the state table only lists 5, so there are 3 unused states. When an input of 0 or 1 is included with the unused present state values, 6 unused state combinations are obtained for the present state and input columns 0000, 0001, 1100, 1101, 1110, and 11111. These 6 combinations are not listed in the state table, and hence they need to be treated as don't care minterms. Using the don't care conditions, we can simplify the equations using K-maps to get the flip-flop input equations to implement the logic diagram. During operation, it's possible that outside interference or malfunction will cause the circuit to enter one of the unused states. Thus, it's sometimes useful to specify fully or at least partially the next state values or the output values of the unused states. So, what to do with those unused states? There are several ideas. 1, the output of the unused states can be specified so that any actions that result from entry into and transitions between the unused states are not harmful. 2, an additional output may be provided or an unused output code employed which indicates that the circuit has entered an incorrect state. And 3, to ensure the return to normal operation is possible without resetting the entire system, we can specify the next state behavior of the unused states. Sequential circuits can be verified by showing that the circuit produces the original state diagram or state table. In the simplest cases, all possible input combinations are applied with the circuit in each of the states, and the state variables and outputs are observed. For small circuits, the actual verification can be performed manually. Verification by exhaustion may not be possible. In these cases, we use simulation. In manual simulation, it's straightforward to apply each of the state input combinations and verify the output and next state are correct. For verification by simulation, we generate an input sequence that applies all state input combination pairs. This is accompanied by the output sequence and state sequence for checking the output and next state values. Optimization requires that the number of clock periods used exceed the number of state input combination pairs by as few periods as possible. This can be interpreted as drawing the shortest path through the state diagram that passes through each state input combination pair at least once. Here we see the results of the simulation for the sequence recognizer. In practice, we use tools such as Xilinx and MTI Model Sim to do this. Thank you as always for watching. Remember, there's no need to like, share, subscribe, or turn on notifications.